In this video, we'll explain how to predict the molecular orbital of oxygen, oxygen 2 actually, oxygen minus, oxygen plus, oxygen 2 plus. Okay, so in molecular orbital theory, we need to draw the molecular orbital diagram and fill in the electrons from atoms. So for the oxygen 2, we have 2 oxygen. So each oxygen as atoms, it has the electronic configuration as 1s2, 2s2, 2p4. Okay, so if you draw the 1s electron, 2s electron, and 2p or 1s orbital, 2s orbital, and 2p orbital, then the configuration will be 1s2, 2s2, and 2p4. 1, 2, 3, 4. Okay, that's one oxygen. On the other hand, we have another oxygen, also has 1s2, 2s2, and 2p4. Now, after having the atomic orbitals, we need to formulate the molecular orbital that is representing the 2 oxygen, one from this side, one from this side, form the oxygen 2 molecules. So I have oxygen on each side. Before they form the molecule together, they are separate oxygen molecule or atoms, and after that they will come together, form the oxygen 2 molecules. So s orbital, 1s orbital will form sigma 1s and sigma star 1s, and the 2s molecule will form sigma 2s orbital and sigma 2s star molecular orbitals. So let's connect them as this. Now the tricky part is 2p orbitals. For oxygen and fluorine and neon, these 3 atoms, when they form diatomic molecule, their 2p orbitals form the molecular orbital. The lowest one is sigma 2px. Above that, it's pi 2py and pi 2pz with the same energy. Above that, it's pi 2py star, pi 2pz star, 2 anti-bonding orbitals. The highest one is sigma 2px star, anti-bonding orbitals. And we connect them as this. And keep in mind that for the nitrogen, carbon, boron, and beryllium and lithium, essentially from lithium to nitrogen, when their 2p orbital form the molecular orbital bond, this 2 pi orbital will be lower than the sigma 2px orbital. Please refer to the textbook in our class material for more details. So once we have the molecular orbital formulated here, we are ready to take the electron from individual oxygen atoms, put them into the molecular orbitals that in the formed O2 molecules. Okay, so for one last orbital in one oxygen, we have 2 electrons. In another oxygen atoms, we have another 2 1s electrons. 2 plus 2, 2 plus 2. We have 4 1s electrons to put into sigma 1s star orbitals. So we have only one way to put 4 electrons into orbitals to fill them up. And the same thing for 2s orbitals, that we fill these 4 2s electrons into two molecular orbitals formed by these 2s orbitals. Now in the 2p, for the 2p electrons, we have 4 on one side for one oxygen and 4 from another oxygen. Totally we have 8 2p electrons to fill in this 1, 2, 3, 4, 5, 6 molecular orbitals. So 8 of them. We start from lowest one. 1, 2, 3, 4, 5, 6, 7, 8. And that's it. We have 6 in the bonding orbital and 2 in anti-bonding orbital. According to the Hahn rule, they have to be parallel and in different orbitals. Okay, now let's look at, and also to represent the electronic configuration in molecular orbitals, we can write in this way. So electronic configuration for O2 molecule is sigma 1s to sigma 1s star to sigma 2s to sigma 2s star to sigma 2px 2 and pi 2py 2 pi 2pz 2 and pi 2py star 1 and pi 2pz star 1, and this part will be added of those up there. Now if you want to calculate the bond orbital, bond order for O2, we need to count the number of electrons in bonding orbital and the number of electrons in anti-bonding orbital. So we have sigma 1s, 2 electrons, sigma 2s, 2 electrons, sigma 2px, 2 electrons, pi 2py, pi 2pz, 4 electrons. So 2 plus 2, 4 plus 6, 10. So we have 10 electrons in bonding orbital. And anti-bonding orbital, 2 in sigma 1s star, 2 in sigma 2s star, and 2 in pi 2py star and pi 2pz star. So 2 plus 2, 4, plus 2, 6. We have 6 electrons in anti-bonding orbital. And we divide this by 2. The bond order for oxygen 2 is 2. And the unpaired electron, we have 1, 2, 2 unpaired electron. Unpaired electron 2. And apparently this is a paramagnetic. So how about O2 minus? For the O2 minus, from O2 molecule to O2 minus, we need to add 1 electron in the molecular orbitals of O2. So the 1 will be added to the top one. So for the O2 minus, essentially we add electron in one of these orbitals, either one. So we put it in here. And after we have this, we have 1 more electron in anti-bonding orbital. So therefore the bond order, we have 2 plus 2 plus 6, still 10 bonding orbital, and anti-bonding orbital electron, we have 10 bonding electrons. And for the anti-bonding electron, 2 here plus 2, that's 4, plus 3, that's 7. 10 minus 7 divided by 2 gave us 1.5. Bond order for O2 minus. And the unpaired electron is 1. So unpaired electron is 1. Okay. Then how about O2 plus? For the O2 plus, we need to get back to the configuration of O2. Let's try to delete one of the oxygen, one of the add electron here. Okay. Okay. Now we have oxygen at the starting point. So this is O2. To get O2 plus, O2 need to lose one electron. O2 lose one electron to produce O2 plus. So it will be one of these electrons because they have the highest energy. It costs the least amount of energy to remove the highest energy electron compared to any other electron with lower energy. So let's get rid of one of electron. Okay, so I accidentally delete all of them, which is fine. Okay, after removing one electron, we have only one electron in pi star orbitals. So let's count. Bonding orbital, 2 here, plus 2 here, 4, plus 6 here, 10. Oh, we still have 10 bonding electron. How about the anti-bonding electron? 2 here, 2 here, 1 here. That's 2 plus 2, 4, plus 1, 5. 10 minus 5 anti-bonding electron divided by 2 give us bond order 2.5. Unpaired electron, only 1. Okay, so O2 2 plus. So from O2 to now we have O2 plus. To create O2 2 plus, we need to take off another electron, which is this one. So let's try to take off this electron. Okay, again, all of electrons are gone. Let's put them back in here. And compared to oxygen 2, O2 2 plus loses 2 electrons. Okay, bond order for O2 2 plus. We have 2, 2 plus 6, still 10 bonding electron. Anti-bonding electron, we have 2 plus 2, 4. That's it. Nothing here. The bond order for O2 2 plus, 10 minus 6, 10 minus 4 divided by 2, 3. It's essentially a triple bond. And about unpaired electron, none. All electrons are paired here. So unpaired electron, 0. Apparently this is diamagnetic. So for the bond order, from highest to lowest bond order, we have O2 2 plus, which is the triple bond, larger than O2 plus with 2 and 2.5, 2.5 bond as bond order, larger than O2 as bond order as 2, and larger than O2 minus bond order 1.5. The stronger the bond, the shorter the bond length. So therefore, the bond length, Length, the bond length we have O2 2 plus, strongest bond should be shortest length, shorter than O2 plus, shorter than O2, shorter than O2 minus. And for the stability, O2 2 plus is the most stable because the triple bond more stable than O2 2 plus, more stable than O2, more stable than O2 minus. Okay, let's conclude this problem. Thank you.